Hi guys, welcome to another Mr. Cuban lecture. Today I'm going to talk about ionization energy, and this goes back to my last video where I talked about Z. And if you remember Z, it's equal to the number of protons, and I'm using the easy calculation on here because this actually pretty much follows the pattern for all of the non-D block elements, and in general it really helps to understand everything. You don't need to do Slater's rules unless you're getting a master's degree and you have a really picky professor who wants to see the extra numbers worked out. All right, or if just you're interested in yourself. All right, so it's the number of protons minus the core electrons, and a core electron is any electron that isn't a valence electron. Okay, and this matters today because ionization energy. Let's go back to sodium. Okay, and when you look on your periodic table, I'm going to use two elements for this. I'm not just going to use sodium. I'm going to use two elements that you could. After this, I can actually highly recommend go online and look up sodium and chlorine and watch videos of them interacting because it's crazy. They just light on fire and they make salt. Okay, so you take these two substances, they react incredibly. They have all this exothermic energy. They produce a bunch of salt. And you wonder why did this happen? All right, so sodium. And I'm going to draw the Bohr model again because it works, and that's really what matters right now. I got 11 protons, then I've got 2 electrons, 8 electrons, and then one little lonely electron. Okay, and the metaphor people use for this is there's a concert you're going to. And in the middle of the concert here is the Beach Boys. I know, you guys are young and hip, and you want to go see the Beach Boys, and this is 1960. And what happens is these 10 fans, yeah, no, you can't go see the Beach Boys, and then it's bingo night. Anyways, and this electron just gets booted off, all right? And so this is sodium. And then let's look at chlorine. And chlorine's, actually fluorine, we'll use chlorine. Chlorine's got 17 protons, okay? 17 protons, then it's going to have 2, 8, and then you'll notice it has the same number of shells as sodium. All right, so this is very important because you're going to have a much larger potential charge here pulling on the same radius. Okay, so if at home, if you have a magnet and you take something to that magnet, let's say you have a piece of metal, right? You can take your piece of metal, you put it on the magnet and it sticks, okay? You take another piece of metal and it sticks. But then, if you try to put a third piece on there, it just falls away, okay? And what you're seeing is the effect of distance versus attractive forces from electrostatic charges, okay? And I mean, and you can see, like, if I have these two here, and they're sticking even after it's gone because the electrons won't light up till I do that. All right. Anyways, so what's happening here is that force, the force it takes to determine whether or not, because if I pull this here, it doesn't start. There's actually a law for this, okay? And for those of you taking lots of physics, you know about this law. It's called Coulomb's law. It's on the AP Chem exam, actually, but chemists do it a little bit differently than physics. So I'm going to start with the physics law, and then I'm going to convert it. All right, so in physics, okay, we have force, and that is the force that's holding up this magnet. And those of you who've done Newton's laws, you'll recognize this is very similar to the universal law of gravitation, is equal to K, which is a constant, all right? In chemistry, K is usually a constant. It can mean equilibrium. It could be the constant for rate of reaction. And here's just a K, okay? And then it's going to be Q1, Q2 over R. And here's where things get a little bit different between chemistry and physics. In physics, I'd put a little 2 here, and it would be squared. So the radius matters a lot more in physics. In chemistry, now you can do some calculus. Maybe you do some partial differentials. What happens is this force becomes an energy, and the R is no longer squared, okay? Because we're measuring energy here, which is in joules. We're not measuring force in newtons. We're making the energy it takes to remove this electron. And ionization energy, I'll write down so you guys, ionization energy equals the energy, of course, the energy in joules or kilojoules. I'm just going to put a J for joules because I hope by now you know that a J is a joules. The energy in joules required to remove 1 electron from a mole of substance. Okay, and you could say atom, you could say element, all right? And it's always, and a thing on here, it's at the gaseous state, okay? So I'll even write that so you don't have to forget. At the gaseous state. Because people might wonder, well, how do you remove electrons from solid copper? The answer is they don't. They melt at the point where it's a gas, and then they do it, okay? So it's the amount of energy. And so what makes sense here is that with sodium, it's much easier to remove an electron than it is for chlorine. And I'm sure by now, if you're studying ionization energy, you've already written the formula, you know, Na plus Cl2 makes NaCl, and you got to put a 2 here and a 2 there, okay? And you know that this Na is going to be plus 1, and this chlorine is actually going to be minus 1. Okay, the chlorine is fully taken that electron from sodium. And this is best explained through Coulomb's law. And you might be wondering, what are these Q's? So R is the radius. That's the distance from the nucleus to this valence electron. Okay, so that's, and they both have a similar number of shells. And what I'll tell you now that you might learn later on to figure out is that sodium is actually much, much, much bigger than chlorine because Z is much smaller, all right? So if I look at Z of sodium, it's going to equal 11 minus 10, which equals 1. And that is the force, or that is the effective nuclear charge that this electron feels from this nucleus. That's the amount that it's being pulled in from the nucleus. Whereas with chlorine, it's equal to 17 minus 10. Now, did you notice this 10 and this 10 are the exact same number? And what's happening here is they have the same core electrons. So if you use Slater's rules, you notice that these electrons do kind of push on each other, but we're going to ignore that today. We're not talking about that today. So that's equal to 7, which is a much, much bigger Z. Okay, it's a much larger effective nuclear charge. It's actually 7. So if you take the energy, I know this is where you go, well, what does Z have to do with Q? One of these Q's gets turned into Z. Okay, you can pick whichever one you want with Coulomb's law. Okay, you can pick Q1 or Q2 because what it is the energy that's taken and it's measured from a positive charge and a negative charge. So this is the positive charge, and then the other one is going to be a 1 because it's the charge on the electron. Because an electron, because we're measuring one electron, the other Q2 is going to be the negative charge. It's going to be the positive charge. So our positive charge here is Z. That's Q1 or Q2. I don't care how you do it. Q2, the other one is going to be electron, which is just one negative charge. Okay, so if you notice, let's assume, and this is wrong, that the radius is the same. It would still take 7 times the amount of energy to remove an electron from chlorine than it does from sodium. And this has huge implications for how the universe works. Actually, every atom Z and its ability to pull electrons determines its reactivity. So what we're talking about here today, and what I wanted to bring a point of, was ionization energy. So when you're measuring ionization energy, all you need to know is the effective nuclear charge, Z, which we already talked about, and then you can plug it into Coulomb's law. And we'll talk a little bit more about radius here, because I got time, I don't do anything else. What you'll notice is that because Z, so this is one of those weird things that you usually, when you get an equation in physics, especially if you're a physics person, you take the numbers, you plug them in, you find out what your leftover variable is. Well, it turns out what you do in chemistry is you measure the energy, and then you calculate Z based on the numbers have, and then you find the radius. Okay, so they actually, through experimental conditions, can find the energy it takes to remove an electron. And what they've discovered is that because chlorine and fluorine and the entire right side of the periodic table, all of these elements that are way over here, right, they actually end up being very small because this Z pulls in these electrons tighter. Okay, it's, imagine the magnet with the piece of metal here, but when it's getting sucked in, remember, most of an atom is empty space, so it gets pulled all the way into the middle. It gets pulled into whenever. There's nothing to stop it from continuing to travel. Okay, so it can go all the way up, into the atom. Whereas the Z with sodium, so small that this electron actually ends up being really far. So its radius is actually really big, which also reduces the energy it takes to take the electron. Okay, so that's a quick 10-minute discussion of ionization energy. Okay, remember to use Z and use the radius. And the radius really only works in the same group. So when you go down group number 1, you'll notice Z doesn't change. What does change is the number of shells. And with each additional shell, the radius gets bigger. And that's why cesium and francium and rubidium have the lowest ionization energies, whereas over here, fluorine has the highest ionization energy. And they don't actually measure, well, they could measure ionization energy for noble gases, but it's not usually discussed because they don't really react. Okay, thank you for your time. I hope you enjoyed this Mr. Cuban lecture. You have a good day.